Thank you all. Thank you. Yeah, let's see how bright it is and what we can achieve. So we're going to talk no more locks. What can we achieve without the GIL? So who am I? My name is Caio Salgado, right? I'm actually from Brazil. I've been living here in Europe like for the last 2 years, but I've been a software engineer for the past 10. So very happy doing that. I'm also studying my master's in University of Porto in distributed and parallel systems. So I really enjoy working with parallel multi-threading, these heavy load tasks, and I want distributed work. And I also love to be here in the PyCon Italy because I really like Italian food, and that mixes two things that I like a lot. Okay, what are you talking today? So the nice thing when I was building this presentation is that I was using this template from Google, and the colors match I built the theme here, and I got these static images, and they're nice because remember me to breathe, you know, stay calm, and like ask ourselves like what we're talking about here, what this Kai is trying to say. So we're going to talk mainly about concurrency and parallelism. Like I like this image because it shows a game. The name is Overcooked. And the name should imply something related to cooking, but it's actually a game related to like source management, right? Resource management and like a kitchen, right? How can you run a kitchen? Like there you have different chefs there, like each chef is like picking some sharing resources, like sharing the ingredients, sharing the cooking pans. And like you have many chefs working at the same time, doing work in parallel. They might be cooking at the same time. And that's like an idea of working, like gives an idea of how this parallelism and working in concurrency. And exactly, if you have already played a game, it's a mess. It's very complicated to manage everything. So what are you talking about then? We're going to talk about multi-threading, right? Working with multiple threads. We're going to talk about single-threaded, right? We're going to talk about the global interpreter lock. What changes, right? New Python version. Is there 1.13 is coming with the option to disable the GIL, but what's the GIL, right? What does it change? What does it mean? And like I want to be talking about this because like as the creator of Linux said, like Linus Torvalds, like talk shit, show me the code. So I'm going to show you a lot of code here. So a lot of tabs changing. And the first example I have here is as easy as it gets, just count to 10 million, and that's it. And the simplest case possible, do that some number of times. Couldn't be simpler, and this is the single-thread way, and I just going to single, and I'm going to count the time. And OK, just let's see what we can do. Here I'm using Python. I'm using Python 12, as you see, like GIL 1, right? And you're going to run the first one. Sorry. OK. Let's see. And you can see here the CPU. Wow, it's going 100%. Here, my computer have like 32 cores. And when I run the program, the first time, let's see, I believe it's simple. I run like 10 times. And I get an error. It's not simple, it's single. Single. OK. And I run for a larger amount. You can see like I have a core that gets 100%. So yes, I'm running the program, single-threaded. I'm using all I can in Python. Let's run for a really big number. And you can see like I have like the CPU cooking here, getting very fast, but only one small CPU is working, right? And what's one of the ideas of the thread, right? The computer is getting hot now. Is that we can do that multi-threading. What does multi-threading mean? It means that we can run each of those tasks like in a separate thread, right? I have 32 of those threads, so whoa, it's going to be like 32 times faster, right? That's the idea. And in Python, it's very easy. Like, it's a bit harder than just calling the function. We need to create a new thread, give the function it needs, and tell the name. You actually like, sorry. Then you create the thread, you have to call it to start, then you have to wait for it to finish, call it join. The documentation is very good, like wait until the thread terminates. And that's it. So as we expect, we should see if I run this program now with multi and 20, like 32, I have 32 cores, right? You should see improvement, and no. There's no 100%, like it's kind of slower, I believe, like it was very fast before, but now it's not running. And yeah, 9 seconds. So it's really weird because like it seems that if I run if I run with just one core, it is faster than if I run with more than one. Like what's going on? Like 5 seconds to run one single core, and like when I'm with multi-core, it's slower. That's the GIL working. That's the global interpreter lock making us work hard here, right? And you can see, like, you can even see the hardware and the number of the CPUs in the sense that the number is not, like, I cannot get to 100%. Like, it stops for me, like, using 100%. The GIL makes impossible to Python to run, Python code to run, like, multiple threads to work at the same time. Only one can work at a time, so no more than 100%. Let's go to my second demo. Because now, like, I'm trying to use a better API to call the like a simpler API. There's the thread pool executor. So here, like, I'm saying how many threads I want working, and like again, the same simple as possible task. In order to use it, I'm going to just give you the n I want and how many threads, so we can see like the GIL holding us back. So if I run the number 2, and I'm going to run for 10 times, and with, like, if I run with one single thread, you can see, boom, I'll get that 100% there. If I run with 2, then you're going to see maybe like 27. Let's put a bigger number here. Okay, you're going to see like 2 threads like get like 150%, so it's sharing the load exactly like 50%. It's not going any faster because it cannot go faster than 100, right? And you can see that, oh, and also there's another thing, right? It's very hard to stop the program. It's not simple. I press Ctrl+C. No, I don't care. Again. OK, it didn't stop yet. Again. So multi-thread is like brings more issues, right? The error handling is harder because it's separating threads. I don't get any speed gains, right? And so what are you doing here? Like, why we are doing this? Like, how can we use this? Oh, and one other thing I want to share is that, yeah, we are sharing this, if I run again, like for one single core and a really big number, you will see that, for example, I got one thread running here, like everything, like on one core, then it shifts to another core. So this is a nice thing that happens that my computer is burning right now, because one of the things the computer tries to do is like to preserve energy, like not spend so much energy, and the hotter the core gets, the slower it gets. So at least like here, it's trying to shift between a lot of cores, not get too hot and not lose performance at the same time. And it may not be straightforward, but like if I add a lot of cores, I distribute the load, so I'm not going to get very, like, the cores are not going to get very hot. Like the share is already distributed. Like I did the OS system of the CPU work for me, right? Okay, stop. But it doesn't stop. Die. Okay. So how nice was parallelism, right? How do we take away using those threads? Where is my pointer? Okay, so what did you get here, right? You got more code, right? We need to write those threads, we need to write the start, we need to write the join. We got slower code, like it's not run that fast at that time. And the error handling is much worse. Like we don't get the number error, right? So why? Why do we have threads in Python? Like why do we have this API, this terrible API? This doesn't make any sense. So if you just take a look at the Python docs, they say like very straightforward, like introduction, and the first thing you see, hey, they are good for I/O, like blocking I/O. So they are good for that, in a sense that here, like there's a simple example of reaching different endpoints, like not actually just zipping, but the idea is that it's getting different endpoints, and using threads, like the GIL, when it reaches some I/O, it releases Python. So okay, you can run multi-thread like this is not Python code. You're gonna just wait for the internet for something else, for some I/O operation. So you don't need to be the GIL will release. Okay, you can run Python, and we can do. I can show that very well in this third one. This is I simply copy and paste the one from the docs, right? And using thread, and if you run, we should see that it works. Where is the pointer? So Python, this is number 3, docs. And you can see, boom, it already started the 3 tasks. It didn't wait for the first one, and then when all of them completed, then it goes to each one of them and finish it. So yeah, that's an improvement. That's something good. If you want to like look at against how it would like if you did not use threads. Run the same program again, and it works. It's magic because I didn't save. Again. Sorry. Nah, yeah. Okay. Okay, without threads, one at a time. It's slower, so if you want to go through this, if you want to tell Python, hey Python, I'm doing I/O, like you don't need to stop here, don't need to wait, let's do something else. Then you can use threads, that's the way they work. And as I said, like this is for I/O, using this I/O, if you remember, we have like the async I/O, which is also made to fix that issue. Like the code is very similar, but we have a couple of changes in the sense that now we use the async word. When you make that call, you have to call await on it. And here I'm using another API for calling async tasks, the task group that works more like a for loop. And I give a task, to create a task for each one of these async functions and get all them working. And for sake of debugging everything for async, well, it works as we did with the threads, right? The idea here is that the async I/O not necessarily use threads, you just use like the wheel, the generator, in order to do that thing so you can run on single thread way. Awesome. So, okay. So, like what do I do if I want performance, right? What do I do if, like, what are threads? Like, is there some way for us to fix those things, right? Is there another way, right, that we don't stop? So yes, there's multiprocessing, right? And with multiprocessing, we can do it. Let's go to the demo 5 that I have here. So let's open it first. The demo 5 is like I'm doing, again, the simple issue, the simple thing of just counting, right? But now I'm using the process. So again, just counting. But now I'm using another API to create process. And process is just like a thread with a couple of differences. We will see them. Is that I submit a function, I have to do the same thing, right? Here I'm using the thread pool executor, so I give how many I want, and it's going to run it. And you're going to get the results. OK, and here I have a like comparison between like running with multiprocess and running with threads, right? I just need to pass the one that I want and thread. So if we go, Python, that's the number 5. Here you can see like, boom, awesome, that's what you're looking for, right? So I'm running multiprocess, boom, okay, it got in 4 seconds. I managed to get all the work done. Like what I was done here, like 320 and 32. I should pick 32 because that's the number of threads, cores I have. You see the other one is still running. It didn't finish yet. What's the other one? It's the multi-thread, right? So no gain here, like no use. And now there's a one say that's when it makes sense to show you the multiprocess, the new thing of Python 3.13, the free-threaded. The idea is that it's possible now to have an experimental build of Python that we can run without the GIL, right? And how do we do that? First, we have to kill. Any time now? Okay. And how do you do that? So I'm using UV. So if you just go UV Python list, you're going to see, if I get that, you're going to see there, that's the C Python 13, and that's the free threaded up there. Yes, there's a different version of Python, different build of Python, the 13, but with the release thread. I want to run here UV install, no need, but I will run source the free threaded version. And we will see again the same example as before, simple process. So, boom, process, crushing my GPUs, running a lot of my CPU, sorry. And now you are running the same one, and again, yes, we got 100%, right? And we got faster. Okay, we are faster than multiprocessing using threads, right? This is the same code. I just changed the Python interpreter, and we get all this advantage, right? And yeah, so advantage, like, what do you mean by advantage? So I'm going to run it again so you can see. You can try to see. Right now, I'm using almost 8 gigabytes of memory. If I run the process, you're going to get to 8. So I got like, almost like 50 megabytes of RAM just because of the process, right? 32 process. And with the threads, the number goes below 8. So this is a nice thing. I'm going to change this to run only for process. I believe it's proc. Yeah, proc. I want to run for the N of 1,000. And I want to run, this is nice, like I want to run for 10 threads, 10 process. So you're going to see probably 10 of these guys going to go up. Yeah. And the memory didn't hit 8 gigabytes, right? 1,000 is way too big. Oh, again, multiprocess also has all the nice things. Let's put this to 300. But now, let's see, like, if I go this number to 50 process, right? My memory goes to 100 megabytes more. If I go to 500, now I get almost 1 gigabyte more. And like the time is still the same. If I go like to 5,000, I get fail. So many files. Like I cannot open 3,000 process. Like I can change things. This is a configuration of how many files the Python code is looking. I can change that to bigger numbers. But even like it's still running. Even like I put like, okay, 5,000 is too much. Perhaps I want 1,000 process, right? And okay, no, I cannot do that. And my memory like spike, like I'm already using 9 gigs, right? So process, yes, they can do the work as threads, some sense, but they get a lot more memory in order to do that. And yeah, I believe like I can get this number to, I want to show a different issue. Let's see if it happens. Yeah, so I cannot show it. So the memory is way too big. You cannot create that much. But if I do this one, like again, using threads, to use threads, I have to use thread. Okay, thread, and I put, again, like, let's put here 300, but I want 5,000. Memory, okay, I got 1 gig, but that's it. Like, I still got it fast, it worked, and I didn't got that much memory. So one of the biggest things and one of the big nice things about using multithreading is the memory usage, right? The memory usage while you're using threads is way cheaper. Threads are way cheaper than a different process. You can spend 1,000, like much more of them. Like I couldn't even build 800 process. I can build like even 5,000, like 50,000. Can I go there? Yes, like didn't break. It's good. You should return me a value in, yeah, that's it, almost the same time. So that's it's almost like not free, but much, much more cheap than going through process, right? So that's one of the ideas, and that's like when you're doing with multiprocessing. Okay, so nice. Okay, we have this multiprocessing. So is it good? It's all fun and games. So I have this example here about like one of the key differences. And it's a very stupid idea to make a counter because you have like a class of a counter and a list. And what are you going to do? You're going to run that multi-threading, right? This is the first example of this one. And one of the nice things about using the free threaded version, right? So I'm going to just change here back to use the GIL version, right? I'm going to run the example. This is the 6th one. So Python number 6. And what do we get? You can see like it's very simple. It's just going to the list, adding a value, and printing. You can see that Python, normal Python, you just have a difference between the order, right? The order goes different between each one of those. but it persists, like there's no gaps in there. Like the values are there, like it's very hard to get those values to go different. Like sometimes, okay, I get this threads working all right. Oh, the last one was different. So that's the thing about multi-threading, like the Python like helps you to get this thing working. 5 minutes. Okay. I'm going to go very fast now, sorry. Okay. So if I change to the other Python, the free thread, you can see like not even that thing can happen. Like I cannot even, I really tried a lot, and I cannot get those things to behave in a different order, right? Python, the free thread one is working very, very much better in that sense. So you got this free threading and see all the properties you get, right? So the problem that I show you right now is what I call the problem of embarrassing parallel. Like it's really, really, really simple problem. Like I can use a bash script to do it. I had a demo, but not. And so we need a better problem, right? One of the advantages of running multi-thread is that that's shared memory, right? You can share memory between those threads and make them work. So one of the examples I'm going to show you guys is matrix multiplication. I'm going to try to show it. That I can do that with threads. So I'm going to show just the code, not word it, because it's a lot of code. And you can see, like, if I go to the 8 here, like, I'm doing this is the naive matrix multiplication, right? So I just, the script is matrix multiplication naive, right? So create the matrix. So I matrix multiplied single threaded. I just go for all of the lines, of the rows, do the multiplication. And I have this one just to multiply one single row, right? So it's going to give me one row. And I have this very easy one that's going to run the multiplication in threads. So each thread is going to run one line. And if I run this guy here, you see that there isn't much gain, right? 7, no, 8. And I need the size of the thing, of the array. I'm going to put 100, right? And oh, okay, nice. This one is running multi-process, and you can see like there's another issue. Oh, here, you run all. Okay, so the single threaded took half a second. There's 0.6. The multi-threaded took more time, so it was slower. And the process was fast, but oh, it was wrong. It came wrong because they don't share. Like multi-process does not share anything. So just going to skip this. So this is the naive version because like what is the issue here? Is the issue that we are doing very little work. Multiplying one single row is very small. And I did this less naive version, right, of matrix multiplication, where now I have a pool of process, and each one's going to get the matrix and subdivide it and make the calculations for that part. So they're going to have a lot of work in those parts, right, to get that working. And that was better, but again, like the multi-threading was not fast. Like, in this example, it was like it didn't get any better. And I want to show you guys all the work that I had like to make it run faster, but I won't have the time. But the thing is like it gets much, much slower. And why is that? So Python is very good. Like it's really trying to help you in the sense of holding your hand and not let you make a mess. So because in this code, I'm sharing here I call it, I'm sharing the matrix A, matrix B in the result. Because of this sharing, Python is working to preserve that thing for everyone, right? Not make it work. So in order for, I take an advantage of the matrices, right? This multiplication of threads. I have to have a different piece of memory for each thread, right? So giving this, I did this using copy. So the interpreter knows we are using different ones. We get that. So I managed to get that much faster. I'm going to run it and forget it. So this is the, okay, run. And you can see, boo, I have things much faster, right? Now I can get code to run faster. Can I put this to 300? Okay. So now I can, I'm able to beat the, yes, I'm able to beat the single thread one. So you might be saying, okay, so like, this is the good thing about threads, right? We managed to make them work. I had a lot of demos. So finally, yes, I managed to get threads fasting. I had a lot of issues doing that. But some of you might say like, what do you have to, but what was the cost? Like the algorithm you had to change, the communication, how to change. You have to work about how is the task each thread takes. But if you know matrix multiplication, you know like that's not how you do it in Python. Like you don't do it in Python code, right? I have examples that I won't show the code, but it's the number 11, and I'm just going to put this like this. No more game. So this version here, I'm using first NumPy. Unfortunately, I cannot use it, this one with the free threaded. I have to use it with the GIL. So this one, I'm using first NumPy, then I'm using the GPU to do that. And when I use the GPU, like, it's not fair. Like, it's really, really fast. Like, here I have, like I can say I have, like, for the NumPy, it took 1.5 seconds. GPU was way, way, way much faster. And, like, it's... the other examples would be increasing the number of matrices, the number of multiplications, and the number of threads. The time it takes for the GPU is 0, is nothing. So again, like why we are doing multi-threaded if like no one's do that hard computation using like more code, slower, worse, and like we have a lot of different tools to do those kinds of things. Like, so why? And the idea is that like if you just look at the path, it's right there in motivation, right? The idea is not to make this heavy lifting with Python, is to do that with, is Python to be the orchestrator of that. Like it's right on the path. Like the GPU is very fast, but it needs data. It needs to do that processing. If I had some examples, you can see like the CPU is working to feed the GPU with that memory, with that things to work. So we need to have Python to work with that. A lot of examples in the path saying, hi, we do AI, but we need Python to work multi-threading in order to share the data and make things faster. So yeah, and one of the things, if you look at that path, the biggest difference is in the garbage collector, how to share the data without breaking things, because how the garbage collector works right now. And yeah, they are trying really hard to make it good, to make you not have to worry about the sharing, the locks, and everything between your data structures. Oof, so thank you.
Thank you so much. More a sprint than a talk. More a sprint than a talk. Yeah. We have a few questions. I don't know if we will have time for all of them. But the first one is, what's the plan for, because basically none of the standard data structures and libraries are thread safe. So what are the thread safe issues with free-threaded?
So there's another PEP talking about the transition, like how to put that as the default way to run multi-thread. And there's a process in order to do that. Like they are, some of the Python communities are looking at the packages that if they support, if they're able to run without the GIL, and how they make to do that, and how to really slowly go to that stage where we can safely run. So we're going to have to check those libraries and see if they work together and get to that stage.
And what are the trade-offs of free-threaded version of?
So I show a lot of issues here. We have much more control about what you're doing, and like take care of like, again, the size of the task you're doing, and how you're sharing data. You have to make it work in a sense that the data you're sharing is like immutable and works with those guys, and like you have to work with the garbage collector in order for it not to worry about the data you're working. You have to kind of know how it looks and what the garbage collector is looking and what it's not looking.
And there are locking mechanisms for, there are locking mechanisms for atomic code execution?
The same ones as normal Python, like you have produce locks, mutexics, and you can do things.
Okay, and have you tried, I mean, in all these experiments, have you tried the solution with sub-interpreters also?
Yes, sub-interpreters is one of the alternatives of running this free-threaded, in the sense that you don't have to worry about sharing that much. Like instead of spawning different threads, I can spawn different interpreters of Python, and those interpreters, like they have a separate context is not that big as a process, but and it has more security, more safeties. That's easier for I believe the C Python to work with, and like not to mangle this. So this is a possible solution. But if you want to really crunch data, like not crunch, but work very fine, you're gonna want to use that shareable data that the single interpreter with multiple threads can give you. So, yeah.
Thank you so much. Big round of applause.